Now, how do I stop recording? I have to go to this thing. Not sure where I was when my computer decided that it was time to restart. When I set it to restart, approximately 14 hours from now, it overruled. Why? Somebody set it to restart in the middle of class time. I don't know. Okay, anyhow. I think we had this, and we were talking about these things and the fact that if you take the derivative of this respect to y, you get mg, which is your gravitational force, and take the negative of that. Well, you get mg, but take the negative, and that's your gravitational force. If you're far from the surface of the Earth, the potential function is this, integrated, obtained just by integrating the g big M little m over r squared thing. But that being negative gives you a positive here, and there's your gravitational force. The integral that you get from the gravitational potential energy obtained by integrating gravitational force, that we haven't talked about yet, but we've talked about. We haven't gotten to that chapter yet. And one reason we're doing all this stuff with potential energy is so we can make sense of gravitational forces, which are very similar to electrostatic forces. Getting into some really deep stuff. Okay, if we take the derivative of this, we do get negative big G big M little m over r squared, which is our gravitational attraction. We take the derivative of this, we get kx squared. And a while ago, I didn't have a negative in front of this. When I took the derivative of 1/2 kx squared, I got kx, and I knew that was not the elastic force, which tipped me off to the fact that I forgot the negative sign there, which kind of illustrates why it's important to kind of understand how things hang together so you don't make, even if you make stupid errors like that, putting the negative there, you don't persist in them, you catch them. Okay. And you got a better understanding. Anyhow, your elastic force is like a negative kx in your elastic force. Okay. Now, ask you estimate u of 3 centimeters and u of 1 centimeter. Well, it's easy to do that from the graph. Here's a graph. This is not a graph of this. It's 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 a generic graph. It might be your magnetic force. The one thing it has in common to do with some of these, this potential energy would be increasing. This potential energy would be increasing. This potential energy is decreasing. Okay. So it's more similar to a graph of this than it is to a graph of either of these. That's kind of important to know because I just remember seeing this graph of gravitational potential energy, doing it at the same time we were just learning calculus, and finding that a little bit mysterious. Why does graph have this shape? Well, duh. It's because it's a 1 over r. We know what 1 over r looks like. Okay. So that kind of looks like a 1 over r. So it might be a good depiction of gravitational potential energy. But not exactly, because I'm sure it did draw the curve exactly like that in that way. Okay. So in any case, at 3 centimeters, we just do a projection. We estimate on the scale we have here. If this is 8 joules and this is 5 centimeters, here's 3 centimeters, here's 1 centimeter. This is 8 joules. What's this? Well, 3.7 joules, 7.2 joules. Okay. So our potential energy, at this stage, I originally lost my mind and called this F. Okay. Because I was thinking ahead to what we're going to do with the force and just made a bonehead mistake. And say I still have an F persistent. Okay. That's an F. This is written as an F. It should be the U. So to get our U average, we could add these and divide by 2, get a reasonable average, okay? And we actually went on and talked about this blue trapezoid that I drew here, which represents what happens between 1 centimeter and 3 centimeters. Turns out the area of this thing would be related to the average value of U. Now, the average value of U is not particularly important, but we're going to do it anyway. And the slope of this segment is going to correspond to your average derivative. Okay, the average rate of change is derivative is a rate of change with respect to x. So the slope would be an average rate of change of U with respect to x between here and here. It would be the average force if the U function was actually linear between here. Average force would be a little less than that because the curve goes down below. And we talked fairly extensively about that. I was calling it U instead of L instead of U. But using our estimates, we calculate an average value of U approximately that's not accurate, but it's close. Why is that? Okay, the average of these is about 5.45 joules. If this is that segment of the curve, and this is the blue trapezoid you just saw, we could say that our average altitude for the trapezoid would be 5.45 joules. And the area within the trapezoid is 10.9 joule centimeters. Okay. Now, the curve is linear. The area of the curve is really a little less than the area under the curve, under the trapezoid. That visually we estimate maybe a couple of percent less. So your average force, or your average U, sorry, your average U value would actually be a couple of percent less than that. But the estimates are uncertain enough. That's uncertain within 2% anyway, so we don't really worry about it in this case. If you have this curve, and this trapezoid, then the area beneath this curve would be significantly less than the area under the trapezoid. Remember, the average value of the function turns out to be the area under the curve divided by the length. Now, the area under the trapezoid, the area under the trapezoid is equal to its average value multiplied by the width. Because of the curve, the average value of U is going to be a little less. And the average value turns out to be the area under the curve, again, divided by the width. So the average value is the area here divided by your 2 centimeters. The area is the integral of U divided by the 2 centimeters. And this is one of the things that people really need to learn better in their calculus courses. The average value of a function is the integral of that function divided by the length of the interval over which you integrate. Okay, so this is kind of important. You want to know this. Okay, that's a formula you have that has a pretty clear meaning. Apply that formula to this situation, and you get something that's very important, and it allows you to estimate average values from a graph more accurately. Okay. So anyhow, now to the question I actually asked, which was to evaluate the average rate of change of U, the average value of the force. So the average value of the force is the average rate of change of F with respect to X, which is the change in U divided by the change in X. And the average value, the average rate of change of U with respect to X, because F is du dx. And we have it. And there's the estimate. And we get this. Okay. And the estimate comes out pretty easily. You just give the estimates of U at 1 centimeter and U at 3 centimeters. Subtract them. Subtract the X values to get the delta X. Divide it, we get 1.75 joules per centimeter. It's negative because this is greater than this. And it better be negative because the curve is downward too. Slope, the average rate of change is what it is. And then that converts easily to negative 175 newtons. Okay. So there's your average force. Now you get the instantaneous force by estimating the instantaneous force by sketching a tangent line here. Not a particularly straight tangent line. It's supposed to be below the curve. So it's a really miserable tangent line. But I was trying to illustrate the tangent line has a little less slope than the straight line approximation. Okay. So slope is approximate F at 2 centimeters. Okay. I'm trying to figure out how to say everything with the time we've watched. Both due to something I did, then exacerbated by computer deciding to reboot itself. I've got a graph of F versus X. Some force, a conservative force. Then on any small interval, let's take this small interval, some delta X interval. The work done by F on the delta X interval is average force times delta X, right? On a small interval, the average force is pretty close to any old force you get on the interval. Okay. Close to any old force you have in that interval. So that we make a big jump here. Work done by the conservative force is approximately equal to the sum of F average delta X's for a bunch of small intervals. Again, this construction ought to be familiar from calculus. That's how you introduce integrals. That's what integrals mean. Shortcutting details, the limiting process and everything should be totally obvious that on any one of these intervals, the conservative force is approximately constant. So that we just multiply F average times delta X, where F average is any old force within the interval. Okay. I've said that. Now, if I have a rectangle, F average by delta X, what's the area? Well, area is length times width. So that's the length and that's the width, but that to be the length and that to be the width. It's okay. The area. Okay. So in any one of these, the area is average force times delta X. Slices isn't a good word, but it's just what I think of right now. Okay. And call these slices, let's add up all the area of the slices. Or, and if you do it in calculus, of course, you make rectangles out of all of these using the sample point. And this approaches the interval from A to B of F of X dx. Okay. Now, the work done by the conservative force, what's the definition of potential energy? Well, I use definition as the definition of change in potential energy. And leaves a question of where the reference point is up to you. It's negative of the change in U. Or the negative of hopefully you can read that. Negative of U of B minus U of A. That's even harder to read. Okay. So that U of X be the integral from A to X, F of X dx. That's U relative to X equals A. And bites, middle theorem of calculus, and so forth. Or fundamental theorem, whichever. I just kind of outlined the way you prove this. To relate this to what you hopefully eventually understand deeply about calculus. Okay, and more or less do to some extent. But do the details of the theory. You see this, and you see that u is the integral of f, and f is the derivative of u. And you see the graphical representation of this. If instead of b, this is x, then the area that's swept out from here to here is u of x relative to this point. And if this is a graph of the magnetic force that you've measured, you can estimate areas and get a graph of magnetic potential energy. Okay. And you can then talk more and more intelligently about the relationship between potential energy and kinetic. One more quick thing. I wanted to relate all this back to these formulas. But we see that this is the integral, the negative integral of kx with respect to x, right? Okay, so we're gonna study some kx's in lab, we're gonna measure some, and then make sense of it by measuring some kinetic energy. We're not going to be able to do this with experimentally unless my grandson's rocket works a lot better than we think. So we could write it up, we're not going to be able to do that. But we can also relate it to this, and this is fairly easy because your force function is mg, which is constant. It's really easy to integrate that. Okay. And the reason I do this today is in your work assignments, dealing with potential energy function, kinetic energy function, dealt with it in the assignment. And this is intended to somewhat clarify that. Okay.